maybe get started, since we all want to take a break. So I think we'll try maybe around an hour and a half, just kind of give me a bit of a waiver. I'll try to keep my eye on the time, but I know we're all suffering after many hours of lectures. So I've thought a bit about how to give you an introduction to a topic called topological recursion. So topological recursion is by now over 20 years old, and as a mathematical field, it's grown tremendously. And of course, as mathematical fields grow, they usually tend to become more and more abstract. Okay? People try to think, what if we generalize this? What if we generalize that? But after 20 years, often, it's almost hard to recognize the subject that you started with. And so today what I'd like to do is to start with this very abstract subject of topological recursion, which I will tell you sort of the big picture of what it's trying to do to compute, but then sort of go back to its roots, okay? And its roots really start with what's called the Tofts topological expansion in large N matrices, okay? So most of the lecture today is actually going to go back to sort of matrix integrals and understand that there's a special type of expansion that happens when these matrices are very large. And we're going to start seeing how we see some sort of topological recursion structure hiding there. And then the next lecture, we'll kind of start more from the general, it's called Einard or Ranton type of topological recursion. We'll see kind of the general structure, but then we'll go back and we'll apply it to this case scenario so we understand what we're doing. So really kind of get our hands dirty. I think there's no reason in 6 hours of lectures to try to give you where everything comes from. It's not going to happen, right? So the best I want to do is for you to get a bit of a flavor as to where this comes from, what it's useful for, and if you wanted to do a few computations, how you would do that. So that's kind of the most ambitious goal. So let me tell you very roughly what topological recursion is. So topological recursion, in its most abstract way of saying it, starts from some given data, and it's a crank that you turn, and it's going to spit out some other data. So the input data is what's called a spectral curve. Okay? So that's why I did my best efforts for a curly S. Okay. So we're going to start with a spectral curve with two functions on this curve called x and y. And then there'll be a special type of differential form of y differential on the spectral curve, usually called the Bergman curve. So this is going to be the input ingredients. And don't worry, today we're not going to really be talking about much of these things. And the idea is that you turn this crank and it spits out a set of more differentials. These are actually symmetric, so they're not kind of the usual differential forms you know about. And they're going to be labeled by two numbers, okay, g and n. These g and n, the type of problems that you can solve with this crank usually always have to do with something that has at its root some sort of Riemann surface, some sort of one complex dimensional manifold, as we learned in this case. And there are usually two types of labels that you can assign to it. So here I tried to draw a little one. You could draw the number of holes in the surface, the genus, okay? So that's this would have genus 2. So that would be one of these genus over here. And there can be sort of marked boundaries over here, and that will be n. And we'll see what matrices also have to do with this today. So we're going to see that there's going to be some sort of notion of genus and n that we can associate to things that we compute using matrices. Yeah.
So maybe just me, but blue is not really visible.
Okay.
Is it just me?
Okay, I want you all to close your eyes for a second and think about your favorite Riemann surface. What genus does your favorite Riemann surface have?
2.
Ah, good one. How many marked boundaries?
3.
I like it. Maybe still visible. Okay, but I'll try to not use it too much. Okay, very good. So there's going to be something that has to do with some sort of Riemann surface with a notion of genus and a number of boundaries. And we're going to see that this kind of naturally arises in this topological expansions of things we compute in matrix models. So what I first want to do today is I'm going to assume you know nothing about matrix integrals. And in particular, the way that you see this topology appear is by something called Feynman diagrams. So for the physicist, this is maybe something that's familiar to you. For the large chunk of mathematicians in the audience, I'm going to assume you've never heard of it or even seen it. Okay? But I think it's a very nice type of combinatorial tool to keep track of. So essentially what it does is that it turns combinatorics and sort of perturbative expansions, basically glorified Taylor series, into pictures. Okay? And this is really what kind of Feynman's claim to fame became. So what we're going to do is we're going to first understand what Feynman diagrams mean. And then we're going to see that there's an alternative to Feynman diagrams, which goes often under the name of a Schwinger-Dyson equation. This is some sort of consistency relation that allows us to sidestep some of the Taylor series perturbative ideas that we have over here. So once we have Feynman diagrams in our toolkit, we're going to understand what happens when we apply them to matrices. Okay? So we're going to look at matrix Feynman diagrams. And matrix Feynman diagrams is going to be something that's very important when we keep track of the size of the matrix, which is going to be n. And we're going to see that there's an expansion in the powers of 1 over n. So as n gets very large, you get a better and better approximation with this. Then we're going to, kind of the same way over here, we're going to trade kind of a separate view instead of Feynman diagrams. We'll look at something that are called matrix Schwinger-Dyson equations. So this will again be some sort of consistency relations for observables in these matrix integrals. And from that, we're going to derive this notion of the spectral curve. Okay? This data over here, we're going to see how that spectral curve data arises from a matrix integral. Okay? So we're going to land over here. So this is probably as far as we'll get to today, and we'll already see a first few useful applications. And then what we're going to do is tomorrow, well, or Friday, depending on how many survive the hike, we will mention how these Schwinger-Dyson equations can essentially be massaged into a very clever way that was done by Eynard and Naranton into this format of topological recursion. Okay? And it's a very powerful way of computing things. And then we'll see that we can actually perform all the work that is very hard to do with Feynman diagrams using directly this topological recursion. Okay? So it's going to be a very, very powerful tool for us to resum infinitely many diagrams, and we'll say what that means later. So at the end of the day, it's very much like Sisyphus. We end by forgetting all the hard work that we've done and forget all the major Feynman diagrams. Okay, very good. So any questions about where we're going, what the general logic is, what we're trying to achieve? Okay. So far, so good. Good. So let's try to start with the notion of Wick's theorem. Okay? So we're going to be doing some things that I think don't require too many prerequisites, which are just kind of one-dimensional integrals. They're even convergent. So we can start with a simple Gaussian integral, something like dx e to the minus ax squared over 2. Okay? And what I'm going to ask is I'm going to ask about what you might call moments of this probability distribution over here. Okay. Physicists might say he's asking for the expectation value of an observable that he would call x to the 2k. Okay. So does anyone know off the top of the head what the answer is here for this integral? We're gonna rederive it.
Square root of pi over a.
Are there bounds?
Well. Minus infinity. We're not going to write this.
I know this one.
Huh? Okay, close, yeah?
Isn't it like just the product of the odd numbers between 1 and 2k plus 1?
Very good. So 2k minus 1, yeah. So we're going to see that there's going to be a 2k minus 1 double factorial. And then there's an a. There's this a that appears. So this a is what physicists actually call the propagator. In Q of t, this is what would be the propagator. This is its sort of zero-dimensional avatar. So the propagator is going to be this object, 1 over a. And it's going to happen k times. Okay? So then we're going to try to understand this formula diagrammatically and where it comes from. So first of all, we can try to understand where this formula comes from mathematically, and then we'll try to see this in pictures again. So what we're going to do is we're going to think about introducing what physicists would call a source. Okay, that's going to be this j. So we're going to take our integral here. We're not going to insert this observable, but we're now going to add this term jx. And why is this useful? Is because as we take derivatives with respect to j, this just brings down a power of x. Right? So we can compute any moment we want as long as we can compute this integral as a function of j. But that's not a hard integral to compute. Because what you can do is you can basically just complete the square over here, right? So what we're going to do is we're going to write this as ddj k. So this z naught is just the normalization without anything in there. So it's like the square root of 2 pi over a, which is the value of this Gaussian integral. And now we can do this trick. So I know for the physicists, this is a very common thing to do. Now what we're going to do is we're going to shift this x by minus this j. Okay, all the colors are going to be tough. Let's try this. A squared. Oh, okay. And plus j squared over 2a. Okay, so this is just literally now the same thing. I just added and subtracted. J squared over 2a, completed the square. Now we notice that because this goes from minus infinity to plus infinity, we can actually shift this. So I'll call this x tilde. And dx tilde is the same. Okay. So now this j squared over 2a comes out of the integral. And this one we can just do. And that's again just the value of a Gaussian integral.
Okay, something when we think an evaluation at j equals 0?
Yeah, sorry. We're going to take an evaluation at j equals 0. Yeah, thanks for saying that. So j equals to 0. So dbj to the 2k e to the j squared over 2a at j equals to 0. Okay. So there's an easy way now that we're going to see this 2k minus 1 double factorial here. So we can always, of course, just write the Taylor expansion of this exponential. Okay. So that'll be a sum L 0 to infinity, 1 over L factorial, j to the 2L over 2 to the L, a to the L. So if we're going to take 2k derivatives and then set j to 0, how many terms in this sum can contribute? Just one, right? Anything with less than 2k will be annihilated, and anything that has L greater than k will die once you set j to 0. So basically, all we have now is that we can just look at the term where j equals to k. Very good. And so this is going to give us that, where do I want to put this? I'll put this up here. X to the 2k. So we take k derivatives, right? So there's going to be a 2k factorial on top over the term now here. So we have a k factorial, 2 to the k, and a 1 over a to the k. And if you just now write this out, you will see that this is actually the same as this 2k minus 1 double. So this is how we're going to... Any questions about that? Okay, so far so good.
Sorry, I just missed what that sum was at the...
This sum over here, this is just the Taylor expansion of the exponential. Yeah. So then we're just going to take 2k derivatives with respect to j and then set j to 0. So the only term that contributes was this one. Great. There's more questions. There's always more questions. People just don't ask them. So if you have a question, you should probably imagine that 3 other people have this question too. Okay. Put it in. Okay, very good. So right now, this is just some factorials. In life, whenever you get integer solutions to anything, you should ask, what is the counting problem that it solves? Okay, that's usually some good future advice. So what is the counting problem that is being solved by 2k minus 1 double factorial?
I disagree. I think that's the wrong answer.
That's the wrong answer. Okay. Well, if you haven't seen it before, let's try to think about it. So let's imagine we have 2k objects over here. So if you want, each one is going to be this little x guy. Okay. I'm going to imagine they have like a little flag coming up. Okay. What is 2k minus 1 double factorial? 2k minus 1 double factorial is all the possible ways in which I can pair these 2k objects. Okay. So what is 2k minus 1? So we take the first guy. How many does it have to pair with?
2k minus 1.
So there's a 2k minus 1. That's the first choice. Okay. So when we do this pairing, we're going to pair it like this. Let's say we pair these two. Okay. Now, how many is this guy have now to pair? So there's 2k minus 2. Exactly. It has 2k minus 3 to pair, and so on and so forth. Okay. So the basic idea is that what this is counting is the number of ways that I can pair two things together. Okay. This is what physicists usually call Wick contractions, and it's going to give rise to the Feynman diagrams, ultimately. So this is a very important part. Okay? So it's the number of ways to pair 2k objects. And what is this 1 over a to the k? So 1 over a to the k, how many pairings are there for 2k objects? There's k, right? There's k of these lines. So each one of these lines, we can attribute a factor of 1 over a. And this is what we're going to call the propagator. So often it's best to kind of maybe redraw this a bit. So what we're going to do is when we see something like x to the 4, we're going to imagine just kind of taking all these little guys with the flags and we just bunch them together. Okay? So these are the same little 4 x's that we saw before. So again, how would we compute this? Well, there's all the ways that we contract. So there's a 1 over a, 1 over a, same over here. So there's going to be a 3 times a 1 over a squared, which you can check if it's this general formula. So we're going to see when we get to matrices that this story is actually going to be changed a bit. And there's going to be a notion of topology that's going to make this 3 equals to 2 plus 1. We're going to have to split those 3 different contractions into topologically distinct ones. But we're going to see the same example and what changes when we have matrices. Okay, very good. So any questions about this? So each pairing is this 1 over a factor. That's what we call the propagator. And each x to the 2k would be a vertex with 2k legs coming out of it. And so what we can do is we can compute these moments by just drawing all the possible diagrams that compute them. All possible pairings. And this is what physicists do in our program. Okay, great. So now, the next thing we're going to do is going to be understand how Taylor series, and what this is called perturbation theory, is also captured by Feynman diagrams. Okay. So now what we want to do is we want to imagine trying to compute this type of integral. So this type of integral is a lot harder to do. This is no longer just a simple Gaussian integral. Okay? And most of your life in physics will be accepting the fact that you cannot do these non-Gaussian integrals. Okay? And you're going to find various clever ways in which you try to compute them. Okay? And this 1 over n expansion is going to be one of them. So let's try to stare at this integral and think about how a physicist would compute it. So what a physicist would do is, what he always does is just to, or she does, is to always just Taylor expand. Okay? That's basically our number 1 tool. So what we do is we see this exponential e to the lambda over 4, x to the 4. And what we do is we just Taylor series this. Okay? So 1 over n factorial to infinity, e to the minus lambda, so a lambda over 4 to the n, x to the 4 to the n. Okay? I'm just doing the Taylor expansion of e to the this part. Any questions? I see some confused faces. We're good. So now, why are we starting to be in business? It's because now what we're doing is we're computing moments in an integral that we actually just computed, right? Now we're actually looking at moments, again, relative to the Gaussian integral. So that's why it's something that we can now try to compute, and then we try to resum this series. So we're going to do something that is not really allowed, okay, especially in these circles. So we're going to switch the integral and the sum. And now, what is this? So these are exactly the integrals that we were dealing with over here. this form x to the 2k, which we now know how to compute. And in particular, we also have a diagrammatic way of computing those things. So what would we do? Okay. So let's just imagine we're doing the first few terms. Okay. So we have this integral. X and x squared over 2. So we've got a 1. Now minus lambda over 4, x to the 4, plus lambda squared over 4 squared, 2 squared, x to the 4, x to the 4, plus etc., etc. Okay. So how are we going to try to do these same type of diagrammatics? Okay, so the first one that we already know how to do, that's just the value of the Gaussian integral. So there's going to be a 1 plus. And now what we do is we just apply what we just learned over on this board. Okay? Which is when you see this x to the 4, we draw a vertex with 4 legs coming out. Over there, we kind of drew them as if they were 4 little separate x's kind of all coming together. But I'll try to stop doing that every time. Okay? So there's a 4-prong vertex coming out. We have one here that's going to correspond to this term in this expansion. So to this vertex, we're going to assign minus lambda over 4. Okay, that's this term that comes right here. So same thing over here. You can see that each vertex is going to come with this power minus lambda over 4. Okay, that's really just, again, this expansion that's coming over here. And now what we have to do is we have to compute the expectation value. So now what we do is we just draw all the possible ways that we can contract these lines together. Okay. So the first one we've already done together. Right? We had these type of diagrams over here. And there were 3 of them. So we're going to have a factor of 3 of these same diagrams. And for, oh, sorry, maybe I'm switching colors on you unfairly. Where's this 3? Where do we want to put 3 in? We'll put a 3 here. And for each propagator, this a, we have a 1 over a squared. Okay? So each contraction give us a power of 1 over a. So there's 2 contractions here. That's this 1 over a squared. Okay. There's some questions. Ask me the questions. It's better that we get good questions now. It's getting confusing later.
Why do we choose to always have this information of poles? Why do we choose to always have this like exit information of like crosses?
So it's 4 because there's an x to the 4 over here. So we always have powers of x to the 4.
Shouldn't it be 4 factorial? Shouldn't it be 4 factorial?
You mean here?
Yes.
That depends on your conventions. So that'll just change what you mean by the symmetry factors of the diagram. But thanks for the question. Yeah. Okay. So yeah, if we had had, for example, x to the 6, we would draw vertices with 6 valent vertices coming out.
But it's a choice at the end of the day.
It's a choice. Well, this is a tool. It's a tool to compute something that you're given. What I gave you is to compute this integral. So right now what we're trying to do is we're trying to compute z of lambda as a power series in lambda. That's what we're doing. So, you get to pick this. This is what a physicist would call the action. So this exponent over here, we call the action. So for us, usually that is what kind of defines the physical theory. So you tell me what theory you're interested in, and then I go and I cry about computing all these diagrams. Okay?
Strictly speaking, for pedantry, we're also going to restrict to lambda positive.
Well, we'll talk about that.
Oh, no.
So, we'll get there. So, let's, well, if you want, we can even mention it right now, before we continue with the diagrams. So, we're just talking about whether this, does this integral make sense? So this integral makes sense certainly for lambda positive, right? Because at large x, this is going to be damped, right? And it's exponentially dying.
You have 2 more questions.
Well,
Maybe you'll
tell me your questions, and then maybe I'll try to answer one of them. Yeah.
maybe you'll get to this later, but I guess so. If lambda is positive, I don't really see how you get the diagrams. Like the diagrams kind of make sense when you have sort of I can interpret these as sort of being, lines coming out of the vertex, right? Like my exponent. But when I do my Taylor expansion, if lambda is positive, then all the, sorry, wait, no, never mind.
That makes no difference, yeah. So here we can put whatever sign of lambda we want, and drawing this x to the 4 doesn't matter on the sign. But you're right to worry about the sign of lambda. So why are the...
Yeah, just one thing. So you are using this model of vertices and edges to compute the integral?
Yes.
So it gives a value?
Yes.
Okay.
Do you want to go over this example again over here, maybe?
I don't want to take a lot from your time, but...
That's okay, right? That's what we're here for. So here what we were doing. So in some sense, in this particular case, we actually know how to do the integral, so it's not too bad. In general, these are much more complicated objects, but I'm giving you the simplest toy model today. So of course, this might feel like overkill, but we're going to quickly see, for example, how in matrix models, there's already a lot of complication that happens, even for these type of Gaussian type of integrals. But right now, what we're trying to do is to try to take an answer that we can already understand and reinterpret it graphically as some combinatorics problem. And the combinatorics problem is by drawing these 4 vertices and looking all possible contractions of the lattice. And that's how we understood what this 2k minus 1 was doing. And then we have rules for what each thing means. So each contraction is this propagator, this 1 over a. Okay, so that's this 1 over a over here. For x to the 4, k is equal to 2. So there's a 2. And then for x to the 4, so we would have 2 times 2, that's 4, minus 1, that's 3. 3 double factorial is 3 times 1, and that's this 3. So the question is, what is that 3? And the 3 are these 3 diagrams over here. 3 possible ways that we can do these contractions. So this is a picture, and it gives out a number. Okay, sounds good. If this 3 is really, we say each diagram is 1 over a squared. So you should think of this as 1 over a squared plus 1 over a squared plus 1 over a squared for each diagram. And the 1 over a is what we assign to the legs. So in some sense, drawing the pictures is computing precisely this number for you. Does that answer your question?
Yeah, thank you. Great. But we needed first to know the answer of the integral before doing this. No?
Well, in this particular case, but like
the opposite.
You could have started the other way. So we could have kind of told you that this is the way to compute it, and you would have found that answer if you want. But of course, that's only an interesting combinatorics problem because it's already the answer to some integral that we want to do. So you can see here how we're already applying it to something a little more complicated. Okay? So, good. That answers your question. There was a question about lambda positive and negative. Okay, so we can get to it. Okay. So what was the question about lambda positive and negative? So note that for this integral, if lambda is positive, then this is a convergent integral. Okay. So at large x, this is dying exponentially. So when you're adding up the integrand at very large x, each time you're adding up something smaller and smaller and smaller, and it converges. Okay. Now what happens when lambda becomes negative? Diverges, right? It's exponentially growing as e to the plus x to the 4, right? So that's not a convergent integral. So what should that maybe tell you about a Taylor series, an expansion in lambda? What does it maybe tell you about the radius of convergence of this series?
0.
It's 0, because at lambda, anything little less than 0, it makes no sense. But for positive, it does. So if you want in the complex plane, the radius of convergence is 0. Or even on the real line, if you want.
Sorry. I mean, the function is entire, no? So it shouldn't have. This function is entire, so its radius of convergence should still be infinite if lambda is.
No. This has 0 radius of convergence as a function of lambda.
I'm talking about the integrand.
The integrand is fine.
Well, we don't care about the integrand. We're asking about the expansion of z of lambda, which is the value of the integral. Yeah. Of course, the exponential is. We're not worried about the exponential. We're worried about once we do the integral. Right? So how is this as a function of lambda expanded? So there's various ways when we look at Taylor expansions to understand the radius of convergence. So one way to do it is, for example, through this ratio test. Okay? So we can look at the ratio of successive values of the coefficients in the expansion of z of lambda as a function of lambda. So maybe this wasn't pedagogically the best thing to get ahead to, but it's okay. We've embarked on this journey together. We're going to finish it. Okay, so what happens here? So what is the coefficient of this series at the nth order in lambda and the nth plus 1 order in lambda? Okay, so I just have to look at this, and then I'm going to do this integral, right, using this result over here. So we already know the result. Then we'll reinterpret it graphically right after this. So at the nth order in lambda, okay, I have to compute the expectation value of x to the 4n. Okay, so x to the 4n, that's going to be 4n minus 1 double factorial. There's a 1 over 4 to the n. There's a 1 over n factorial, and there's going to be this propagator, this 1 over a to the 2n. Okay, so that's the general coefficient of order lambda n. So now what we can do is we can look at the ratio of two of these coefficients. So this is Cn plus 1 over Cn, and we ask for large n. Okay, so high orders in the Taylor expansion, what does this ratio look like? Is it getting smaller or is it getting larger? And the ratio of these two things is actually growing with n. You see this 4n over here. It's growing linearly with n. So that means that each time these coefficients are getting bigger and bigger and bigger. So you're trying to sum something where the coefficients of the Taylor expansion are getting bigger. Okay, so that's not going to converge. Okay, so this is what we call an asymptotic series. An asymptotic expansion. And there's going to be something truly remarkable that happens once we introduce this 1 over n expansion, is that the expansion in the coupling is actually going to be convergent. It'll have some finite radius of convergence, but it'll actually be a convergent expansion. So that's really one of the beauties of the results of Toft. Okay? So this was a bit quick, but at least it tells you. So this is why I was worried in front of you to publicly exchange the integral and the sum. Because what this is telling you is that this is not an okay thing to do. Okay? For lambda positive, this is something that makes total sense. But you see, this expansion, even for lambda positive, is going to be a bad expansion. At some point, the approximation will get worse and worse and worse, and you're going to be very far away from the true value of this set of lambda. Very good. Okay, so let's take a breather. Now we're going to go back, and we're going to try to understand how we're going to use these Feynman diagrams to compute some things about this integral, but then also about moments. This more what physicists would call interacting theory. So I'll use the word sometimes interacting. All that means is that we're adding something in this exponent that is not quadratic. For all intents and purposes, for mathematicians, that's all you need to know. And for physicists, you probably know what I mean by interacting. Okay. So what we're now trying to do is we're trying to go back to this expansion and just reinterpret it graphically using the pictures that we draw on the first board. Okay. So we did that over here. So this first term, okay, that's just going to be 1. Then this x to the 4 is this quartic vertex. When we do the integral, we do this pairing. It brings down a factor of 1 over a for each pairing. So that's this 1 over a squared over here. And this factor of 3 came from the same factor of 3 over here. There's 3 possible pairings. So now what we want to do is we want to look at them for the second order in lambda. We want to possibly draw all diagrams. There's only 2 distinct topological type of diagrams. So I'm going to get rid of this now, I think. So there are 2 types of diagrams that can happen. There are the ones where we basically just connect. They're all sort of self-connected, and they just kind of are. They're what we call disconnected. So let me draw these type of diagrams. They're going to look something like this. And how many ways were there of doing this? There were 3, right? The same type of diagrams we did over here. So there's 3 such type of diagrams. Same over here, 3. So the number of these disconnected diagrams is going to be 9. And then there's going to be a different type of topological class of diagrams. Okay. So we again have these type of vertices. But now we can pair some of these guys together. Okay? So there can be something like this that happens. So what was that doing? Propagators in red. There can be these type of diagrams. There could even be these type of diagrams. So maybe I'll draw them a little closer. And then we have to think about the various combinatorics of these diagrams. So how many are there of each case? And okay, do I want to do this completely? Yeah, I'll just answer for a second because it's not going to be the most important. I'm just going to tell you that the sum of these is going to be 96. We can work through the combinatorics, but it's somehow not really the most important part of the lesson. But I wanted to at least separate out these type of diagrams that are connected versus things that are disconnected. You can just kind of pull these 2 guys apart. Okay. So if you add, for example, 96 and 9, okay, and then we compute how that compares. So 96 plus 9. Okay. Versus, so this is the second order. So this would be x to the 4 times 2. So that's 8. Okay, so this is 7 double factorial. You'll see that this is indeed degrees. Okay. So those are the total number of the contractions, but we're going to separate them into connected and disconnected. We're going to see how that actually is going to be important for us. Okay, maybe that was a little too quick. Would it be helpful if we go through the combinatorics of these diagrams? It's not really that important, right? Combinatorics, you can always kind of convince yourself one way or the other. You know, someone tells you, oh, but there's a factor. Anyways, there's a right answer, but it's not really going to be what we're trying to get to. I'm just trying to give you a way of saying that if you count all these type of diagrams, there are 96 of them. Here there's 3. Okay, so we can work through that. What I did want to get to is to understand the notion of connected diagrams even further. So connected diagrams, from one sense, it's very simple. These are just the things that are graphically connected. There's another way that we're going to see this kind of connected contribution appear. So let's imagine we now want to ask about the second moment of this probability distribution. Yeah.
Like with the philosophy of before, you could actually draw one vertex with 8 legs, right?
Yeah, so that's
but
just...
you have this 1 over 2 factorial. Is it this why you have 2 times 4?
That's right. Because there's this n factorial here that tells you should really have n vertices. And the n 1 over n factorial is the permutation of all the n vertices. And of course, in a field theory, these would be labeled by some positions. So you would tell the difference between x to the 4 position 1 and x to the 4 position 2 instead of, but here we're in 0 dimensions, so these things are, you can't really tell them apart. Yeah, but great question. Okay, good. Let's imagine we wanted to now compute the expectation value of x squared in this probability distribution over here. So what that means is we're now going to insert an x squared in this integral. Okay. And we're going to divide by the value of the integral just so that it's a normalized probability. So here we were just trying to compute the integral. Now what I'm doing is I'm inserting x squared the same way that I inserted x to the 2k in this integral. Is that clear? Yeah? Okay, good. So how would I compute this? Okay, so we can again think about computing this back into the Gaussian. So lambda equals to 0 is this Gaussian case. So we would have this e to the lambda over 4 x to the 4, x squared. And this is just the value of this z of lambda, right? So this here It's just 7. And I would again do perturbation theory in this lambda. Okay? We would have a 1 minus lambda over 4x to the 4. That was this first term that we were looking at over here. Same over here. But now it's going to be multiplied by x squared, which I inserted into the integral. So now we see we have a ratio of things, and what we want to do is we want to just expand this ratio in powers of lambda. So the first thing is just going to be x squared to order lambda equals to 0 divided by 1. So this is just the lambda equals to 0 answer. To first order in lambda, we can either have x squared times x to the 4 up here, or we can have the term from lambda where we expand this now. Okay? So the first one is the lambda piece up here, x4 x squared, x4 x squared. Or we could have the x squared times 1, so that's the x squared times 1. But now this guy, once you expand in lambda, comes in the numerator. Right? So that's going to be this x4 over here. Now we're going to understand what this difference means, okay, in terms of diagrams. And again, it's going to have to do with connected versus disconnected. So what I'm trying to get at is that when we want to actually compute moments of some distribution, we actually only need to look at the connected diagrams. That's going to be essentially the takeaway. Later, when we draw diagrams, we never have to worry about things that are disconnected like this. We always just draw one single diagram that's connected. So, okay, how would we think about this? So now we're going to draw... Is there another question? Yeah, okay. So now there's going to be two types of vertices, what are called internal and external vertices. So the vertices over here that I'll try to keep in purple are the internal vertices that just come from the expansion over here. So the powers of x to the 4 that come down when we do this expansion. But you see, there's also an x squared that I externally put into the integral. Okay? So I call that an external vertex, and I'll try to keep those in white. Okay? So the first one is just this value of x squared. So it's just this wick convention over here. And that will be a factor of 1 over a. But now we have two different types of things. So we have this external guy, this internal guy. And either we could have a contraction like this, or we could have contractions where these legs go onto the purple ones. What is this difference telling you to do? So what would this look like diagrammatically?
Asking for it to always have two connected components?
It's asking for, you're basically subtracting off the piece that is disconnected. So you see this guy is x squared on its own. And this x to the 4 over here is something that's just on its own. So it's also just a disconnect diagram. Whereas this includes both possibilities, where we always have to sum over all possible ways that we can draw the lines between the lines, right? So what this combination is telling you to do is to actually only keep the diagrams that look something like this. Okay? And other types of contractions, but at least when a white guy is always contracted with one of these purple vertices. Okay? So this is the notion here of a connected, fully connected Fourier diagram. So this particular example, you don't have to follow all the details. I'm just trying to motivate, I use this example to motivate to you why later on we're only going to look at connected diagrams. Okay? That's all you need to know. And roughly what it's saying is that this denominator always subtracts off all the disconnected pieces. So in some sense, dividing out by that denominator always gets rid of those graphs where these things are disconnected. Okay, that's it. Okay, very good. So, let's pause here and let's get through some questions. I'm sure there's at least 2 questions. So first of all, let me understand how many people had seen Feynman diagrams. Okay. Wait, it's also way more than I thought, actually. Okay, good. So now you can ask some questions, yeah.
Okay, my question is, does this cancellation of disconnected diagrams always happen? Like, can you actually prove it that no matter what, I guess, weight you put in there?
Yes. Yes, that always happens, and it's just too much for us to look at today. But there's a theorem about the exponentiation of these connected diagrams. So in particular, actually, for example, one thing I taught last year is if you look at the log of z of lambda, and you do an expansion of the log, what you find is that the only diagrams that contribute are actually these connected ones. And that's also a theorem. The log of what we would call this partition function is actually only a sum of connected diagrams. So there's a similar theorem.
Why are we no longer worried about this expansion being bad?
Oh, well, I'm worried about a lot of things, but yeah, I mean, if this is when you stay up at night, it's a good life, but no, we should be, this is a bad expansion. This is an asymptotic expansion. And in particular, if you really computed these things, you would actually see that you're getting, so this, it turns out you can actually compute this integral in terms of some modified k Bessel functions. And so you can actually try to look at how good your Taylor expansion is relative to the exact answer. And you'll see that after a few orders, as you go to higher order in lambda, you just get worst results, which is kind of symptomatic of an asymptotic expansion. So no, you're still worried. It's just that usually this is the best tool we have. But we're going to see how this large n expansion is going to do a lot of work for us. Or we're going to get something convergent.
So could you explain again how you went from the ratio to the subtraction?
So I just basically, yeah, sorry. That was a little rude. I just used that 1 over 1 minus epsilon for small epsilon is 1 plus epsilon squared. So the epsilon squared. So I was just using implicitly, I was just expanding in this small number lambda here. So you have a small number, you have an expansion in lambda up here, an expansion in lambda in here, and you just now again do the Taylor series of the numerator and denominator.
And then I will get the subtraction.
Yeah.
Okay.
And the sign comes precisely from this type of sign difference here.
So maybe a comment about the bad nature of the expansion. Like once you calculate this asymptotic series, then like, there is tools that you can use to kind of undo what you've done to turn it into like a convergent expansion. So you can use like Borel resummation techniques. So in fact, it makes sense to calculate it, even though you know that it actually doesn't converge, but you can do something to it after that, and you can recover the Bessel function in this case.
So essentially we're just treating it as a formal power series at this stage?
Yeah. And usually the first few terms are not terrible. So like physicists compute things like this, and then they measure things that they'll see, and it's usually pretty good. So, like, but there's a lot of fancy ways of doing kind of partial resummation techniques, so things also called like Padé approximants and things like that, if you've maybe come across that. There's fancier things that are non-perturbative about Borel resummations, where you get e to the minus 1 over lambda type of effects. So there's a lot of interesting things that can happen, but this is kind of the most basic no graphing needed. Okay, good.
Yeah, I think I couldn't understand what totally connected diagram is and how do we get...
Yeah. Really what I just mean for now is that there's a notion of connected from probability, where you basically are going to subtract all the individual ways. So in general, what we mean about some connected... blue is that, right? Yeah. So things like this. We would usually mean this is AB connected minus, well, sorry, write it this way. Connected. So, and when you have more and more objects that you're computing their expectation value of, you need to basically subtract all the various ways that you can kind of single them out. So you sum over all possible various permutations, like sort of, not permutations, all possible subsets of objects in here, and you subtract off their expectation values, and that's what we would call fully connected. In this simple example of two things, this is just the...
But can we go over the diagram argument again? Because like the diagram the x squared is just, as you draw there, it's just a circle.
Yeah.
And the x4 wasn't it just like that?
It's these type of diagrams that we do.
Exactly.
So there's 3 of them as well. Yeah, I just wasn't drawing them.
And how do we multiply them? Like, what does...
It's literally, I mean, each diagram is just some number, right? It's like 3 over a squared. So multiplication just means multiplying these numbers together.
But I see, but we somehow derived some kind of a geometric meaning out of it. I couldn't see the
Right, so I'm saying here what you would do is you would need to sum over all ways that you could tie these legs together.
Oh.
And in all of the ways, some of them are going to look like this, and some of them are going to be connected. And what this expression is doing is it's precisely subtracting the ones where they're disconnected.
Okay.
So this combination is something that we can compute only with these connected diagrams.
Thank you.
I was a little schematic.
So with the resummation technique you talked about, can you make sense of any order in perturbation theory, or is there a point where even though you try to resum this, the rest of them, it doesn't work?
There's no free lunch. I mean, these Pade approximants are very helpful and they're powerful techniques to improve your approximation, but you're not going to turn an asymptotic expansion into a convergent expansion.
So at some point it means that like theorists won't be able to provide experimentally like good enough precisions.
We run into these issues. I mean, we're already getting close to those type of problems in QFT. So people now do like 8 loop diagrams, which means order lambda to the 8. And it's unclear where things get better or worse. So people have increasingly tried to find new ways of getting better approximation schemes. And particular, actually, the original motivation of Tilft was for gauge theory, so for particle physics, to come up with a new approximation scheme. So it was to try to find some new parameter that he could make small that was not this lambda. And we're going to see it. Okay. Any more questions about this? So what I'd like you to take away from this board is that it gets hard very quickly. Okay? So that's all you really need to take away from this. You can see, if we go to higher and higher order in this lambda, there's going to be more and more, right? There was already 7 double factorial possible ways that, possible types of diagrams here. Right? This very quickly gets out of order, okay? So, you know, an easy way to ruin your life as a grad student is to just compute these things to higher and higher order. So what we want to do is we want to try to find different ways that are not just basically using perturbation theory. Okay? So this next board is going to be try to find a consistency type of condition. This is often like this type of idea called a bootstrap, and it's a kind of a baby idea of a bootstrap, which is we try to find some consistency condition that's not going to be perturbative in this lambda. And sometimes it's easier to solve those type of equations. There's maybe one thing you need to calculate, and then you can calculate everything else. Okay? But it's not a perturbation theory in lambda. And ultimately, topological recursion can be thought of as a way of resumming all of these diagrams. Okay? So at the end of the day, we're going to forget about Feynman diagrams, and we're going to find this very cool recursion relation that is non-perturbative in this coupling lambda, for example. Okay? That's where we're headed. Okay, very good. So all you have to remember is that there's Feynman diagrams, and it gets hard quickly. Okay. Very good. So let's talk about a Schwinger-Dyson equation. So the basic idea is going to be starting with this type of identity. So we're going to try to say that the total derivative, the integral of a total derivative is going to be at the boundary. So we want something, we'll take our little example over here. So minus ace 2. I'm going to give up on the colors for a second. Over to x squared minus lambda over 4 x to the 4. And here what we're going to do is we're going to imagine putting in x to the k plus 1. Okay. So the boundary term would just be this, and this at x goes to plus minus infinity vanishes. Okay. So what we see is that we're going to get a consistency relation by saying that 0 is equal to this. And it's going to give a recurrence relation because we're going to act with this derivative on various terms in the integrand. So let's just kind of do this together. So actually, you know what, let me put a 2. It's a little nicer. So what happens if we do this on the first guy? So on the first guy, this is going to bring down 2k plus 1, x to the 2k, times this guy. So that's when x here. And when we do the integral, I'm going to just divide by the normalization of this integral. That gives me a 2k plus 1. And just the expectation value of x to the 2k. It's going to be the first term. The second term is where this derivative can now act on the exponential. So there's going to be the x to the 2k plus 1 up here. There's still the exponential. And now there's going to be the derivative with respect to that. So there'll be a minus sign, ax minus lambda x cubed.
Sorry, the thing you divided by is z0 or is that?
This is the...
It's lambda, okay.
Yeah. The value of this value. So what do we have? We have now a minus x to the 2k plus 1 plus an x over here, so 2k plus 2. And then a minus lambda x to the 2k plus 1 plus 3. So 2k plus 4. And note this is a relation that is not at all in any ways perturbative in this lambda, right? We didn't need any Taylor series or anything like that. But now this gives you a relationship between various moments of this probability distribution. So it's our first recursion relation. It's not topological yet. So let's do a simple one where we, for example, take k equals to maybe 0. So let's look at the k equals to 0 case. Okay, so there's a 1, x to the 0, so that's 1. It's also just 1. Minus a, so k equals to 0, so this is x squared. Okay, minus lambda x to the 4 is 0. Okay. So this is just 1. So for example, it tells you that I could figure out x to the 4 in terms of x squared. Okay. Now if we go to the next one, k equals to 1, you'll find a relationship between x to the 6, x to the 8, and x squared. But so as long as you knew x squared to start out with, you could actually determine all of these moments successively. Right? So here what this is telling you is that once we know x squared, then we have all others. Now, in general, this could still be a hard problem, right? Like computing x squared. It turns out, in this case, you can compute this integral z of lambda, and we use a as the same way we use this j over here. We can take derivatives with respect to a, and then we bring down a factor of x squared. So because that integral can be done in terms of these Bessel functions, you can take derivatives of Bessel functions, it turns out you can actually compute this x squared. And then from that, you would then have all the higher moments, starting from this base case of x squared. So do you see how that's infinitely easier than trying to do what we struggled with so much here, doing just to order lambda squared? Okay? Now we're getting answers that are going to be full power series in lambda. So the idea is to try to find some sort of relationship between observables that is not perturbative in the parameter lambda. And that's the main idea behind topological recursion. Okay. And what we're going to see is that what plays the role of the data that you need to know in the beginning is precisely that spectral curve over there. Okay. So the spectral curve data is going to be everything you need to kind of start your recursion life. And then you just compute recursively, and you get functions as a full function of these companies.
This still only works for lambda positive, right?
Yeah, let me think. So what goes wrong?
The integrals are not defined on the boundary.
Yeah, the integral just probably won't. Yeah. exactly. This will not be true when lambda is negative. That one. This relation is wrong. Okay, very good. So we haven't talked about matrices, large N, topological things yet, but sort of all the avatars of these complex ideas of topological recursion are already hiding here. Okay, we're going to see the Feynman diagrams. The reason I introduced Feynman diagrams is because it's what connects matrix models to topology. Okay, there's no sense in which there's going to be a topological expansion unless we look at these Feynman diagrams. I could have just kind of told you there is, but it would have made no sense for you. Okay, so that's why we had to struggle a little with the idea of Feynman diagrams. But then ultimately our goal is to kind of move beyond them and to find new type of ways like this where we don't have to actually compute all these graphs. Okay? So here is, I think, maybe the simplest example where you see both of these ideas and you can kind of see them interplay. So any questions about this? Yeah.
For this condition where you derived these like relations,
Yeah.
is there any significance physically, like as to what these are?
So it depends, well, yeah, this integral probably is a little too stupid to have real physical significance. But there's maybe more like statistical mechanics. These type of relations can also give rise to things like the virial theorem, which is a relationship between like the kinetic energy and the potential energy. People have been using this a lot recently in what's called also the large N matrix bootstrap. So in conformal field theory, which we'll hear about later in the course, maybe was already alluded to a little in the StatMech, there's also a set of consistency conditions like this called the conformal bootstrap equations. And they arise, they're again sort of not perturbative. So people sometimes try to solve these things on a computer. They basically make guesses for x squared. They solve for these type of recursion relations. And then they see whether there's some positive definite properties that are, I'm not going to go into the details. But you can sort of create a matrix that has to be positive definite. And if you had bad guesses for x squared lambda, that would not be the case. So you could rule it out. And what people do is they make more and more guesses for x squared. And at some point, you actually start seeing that one guess basically always works. And then that's one way of solving the theory. So, and something like this also has now been done in what's called the matrix bootstrap. So people try to solve large N theories a bit like this.
Thank you.
Okay, so I think probably that was a lot of information to digest. So now I think is a good time for the coffee break. We'll start a little early. And then we'll come back and we'll do now all of this again kind of for matrices. So we're going to see the Feynman diagrams of the matrix models. We're going to see kind of an avatar of this Schwinger-Dyson equation. And we're going to find a way that we can, for example, resum infinitely many diagrams. And we land on what's called the spectrum curve of the matrix model. So maybe come back in like, let's say 15, 20 minutes. Okay, I think we're all mostly back. So let's now try to actually see how topology of topological recursion is going to appear. Okay, so this goes back to a really beautiful observation that's almost 50 years old due to a talk. So, and we'll see that there's going to be, what he was thinking about is finding a new expansion parameter that was not this coupling constant lambda we saw over there. Okay? Because we saw that perturbation theory in that lambda, no bueno, right? So what we want to do is we want to introduce some sort of new variable. And what we're going to do is we're going to, instead of taking our little variable x, we're going to promote them to n by n matrices. And we're going to see that the size of the matrix is now a new variable in whatever we're discussing, right? Which we're going to call n. And we're going to see that in a large n limit, we can now take an expansion in 1 over n. N is large, 1 over n is small. And that's going to be a different expansion than the expansion that had to do with this lambda that we were doing earlier. And what we're going to see is that this 1 over n expansion is very intimately connected to the topology of the Feynman diagrams. So that at any order in 1 over n, we're going to see that we only need to look at Feynman diagrams of a specific topology. So what n is doing is it's keeping track of the topology of the diagrams. And that's where the connection to topological recursion is going to come. Okay. So the basic idea is we're going to start just like what we were doing. We're going to promote this little 1x to now an n by n matrix. Okay, so we're now integrating over Hermitian matrices. So I'm going to assume that m is equal to m dagger. And these mij's just denote the various entries. Okay? So when I'm integrating over them here, what I'm integrating in is I'm integrating over all the independent entries in this matrix, both their real and their imaginary parts. Okay, and along the diagonal, they're real anyway. That's not going to be too important for us right now. Okay, very good. So that's going to be the main idea. And we're going to see that this n also enters in the propagator. Okay? So where we had this dx e to the minus a over 2x squared, that's now where the size n is going to appear. And that n actually is important for this to have a well-defined large n limit. Okay? So right now I've put it there as if God-given. Just trust me that it's sort of needed to make sense of the theory. Okay? Very good. So the first thing we want to do is to understand just the second moment, right? So the Gaussian is all determined by its second moment, which is basically how wide the Gaussian is. Of course, that's basically the Gaussian. So the propagator was just telling you about variance of the distribution. So you want to do the same thing for m. But now we have n squared variables that we're integrating over. Okay? So this propagator is going to be a little more complicated. And now when we look at a variance, we can actually choose which of the n squared variables we want to look at. Okay? So what we can do is in this integral, we can choose, add in, say, mij or some other entry, mkl, okay? Which would define what we mean by this object over here once we normalize the integral. So we're going to ask now about this two-point function. So that's physics term, but yeah, so physicists would call it two-point function, two because there's two of these m's that appear in the expectation value. We're going to ask, what is the expectation value of that? Okay. So first of all, what can we sort of tell? We can tell that because the same way that n appears, this is actually going to have to be inversely proportional to n. Okay. So if there was an a over here, this is a 1 over n that's going to appear over here. But now, are actually all of these correlated? So is M17 and M918 as matrix entries, are they correlated? Well, how would we see that, right? We would look at these integral over here, and let's write this trace of m squared out in the various matrix entries. So trace of m squared, we do matrix multiplication, and then we sum over the last two indices. Okay, so it looks like this. For the rest of this lecture, one second, I'm going to drop this summation sign. Okay, this is what we call Einstein summation convention, that if you see repeated indices, that means that they're going to be summed over. So we'll just implicitly assume that for the rest of this lecture. If you ever get confused, just ask me about it. Okay. You had a question?
Are they random matrices?
So in some sense, we are integrating over all possible matrices, right? And we're actually, the same way that we could think of this as a probability measure on X, we can think of this here now as a probability measure on the space of Hermitian matrices. So that's a bit the perspective we discussed last year. I mean, you weren't here. But I just didn't want to repeat that so much. But this is the starting point of random matrix theory. Okay.
Like, how do I express this measure? Like the implicit measure work?
So it's the product of dm II, so along the diagonal, and then the real and imaginary parts of, say, the upper triangular parts. Because the lower triangular are related by the Hermiticity condition. So you just have n things, and then n minus 1 over 2 variables for the reals, n minus 1 over 2 for the complex piece, for the imaginary part. So there's n squared number, just n squared variables that you're integrating over. So now let's look over here. Okay, in this expression, do you ever have m1 7 and m5 19 appear in this sum? No, right? because this index is always the same as this one, and this one over here, right? So at most you can have things like M1, 18, M18, 7, or 1 that are correlated, right? Okay, so what does that tell us about this expectation value over here? It tells us that these two indices and these two indices have to be the same, right? I, J, J. So when we see an expectation value like that, it says that it's 0 unless I is equal to L and J is equal to K. This is the 2-point function of this little matrix integral. And we're going to draw this the same way that we looked at pairings earlier in the Wick contractions. We're going to draw this as a line. Except now it's no longer just going to be a line. It's going to become a ribbon. This is the ribbon. And why is there a ribbon? It's because instead of just x, we now have something that has two indices. Okay? So this is an m over here that has ij. So we distinguish the rows and the columns. So there is some orientation to these lines. And this would be mkl over here. And what this little ribbon means is precisely just computing this 2-point function in this integral. So it's just a picture that says compute this integral.
What about this direction that you put on the lines?
So that was about which one is a row versus a column.
Okay.
So here I picked that rows outgoing. Yeah. Okay, very good. Now I want to do our first little computation of the expectation value of a trace of some power of the matrix. And I want to do it in very close parallel to what we just did with our little 1D stupid integral. Okay? So let's just try to, so you're going to see these things look almost identical, so that it's not going to be too hard. So look at this type of pairing that we were doing. So we wrote something like x to the 4, and we draw 3 diagrams. I just want to maybe highlight, just in case it wasn't clear again, that what we're doing is we're basically breaking up this expectation value into a sum of products of pairs, okay? So, for example, when we drew something like this, okay, what that meant is that we had an expectation value like this, x red, and then next screen. And similarly for these other terms. So I don't think we need to go through all of them, but these are just all the various ways that we could contract, right? So this means that we have a yellow and a red, a yellow and a green. Etc., etc. Okay? So really what we're doing is we're just taking this and we're just looking at all the possible pairings. This is what we just said earlier. I'm just drawing it one more time so that it's clear. Okay, good. We're going to do it. Now let's now just apply this rule for all the ways that we can compute these 4 objects. So now what we want to ask is what is the expectation value of trace m to the 4? So again, that means I put trace m to the 4 in this integral, and I do the integral. So here what I've done is I've just written out the matrix multiplication and the trace in terms of the indices, the individual matrix elements. Okay? NAB, BC, CD, DA. So the last and first guy implement the trace, and the rest is just matrix multiplication. Any questions about just notation or anything? Okay, very good. So now what we're going to do is we're going to take these four elements and we're going to break them into the pairs. Okay, so we'll have an NAB. We could, for example, do NBC, NCD. So now I got this guy with this guy. And we could have this one and this one. So NAB and CD. too ambitious with colors. Are the mathematicians struggling with the repeated indices, or are you good with that?
Depends on if they're geometers or not.
Geometers, are you okay? You doing okay? So let's now just use the rule that we had over here, right? Okay. So this guy is 1 over n. Right? That's this 1 over n over here. Delta AC, delta BB. Over here, delta, so there's a 1 over n, delta CA, delta DD. I know this seems slow, but hopefully I think you're going to see these. There's going to be different powers of n that appear. That's going to be very important for the topology. So AD, BC, delta CD. Now, let's just do the sum. Okay? So you can tell me what the values of these sums are. So we have a 1 over n squared, just from these guys. Now, what is delta BB?
N?
That's the factor of n, right? So the factor of n, because you're summing just along the diagonal of the identity matrix, right? So there's a factor of n that's appearing here. There's going to be a factor of n that appears here. Then this gives you sum over c, delta AA. There's one other factor of n from delta AA. So then we get an n cubed. Is everyone on board with that? Very good. Now, so we have a 1 over n squared from the propagators. Now what happens over here? What's the power of n?
So you sum over with delta BV.
We can do, say, this guy and this guy and this guy. So it's going to give us a delta AC. With this guy, gives a delta cis B. Well, can do it in steps if you want. So this and this gives us a delta AC, delta BC, delta BA. Sum over B, this gives you a delta CA. Okay, and then this gives you a delta AA. So how many powers of n do we get from the sum? It's a single power of n. Over here. Cubed. So there's an n, and these two guys will give you an n. So there's an n cubed here as well. So here we're starting to see something interesting, right? These three diagrams are actually no longer the same value. Right? So remember over here, each one of them, okay, this last one missing, so this guy. This just gave us 3 times 1 over a squared. Right? But now what's going to happen here? Here we're going to see that they're no longer on the same footing. Right? So we have 2 of them that are on the same footing, and 1 of them which isn't. Okay? So this is going to be, so there's a 2n, so that's this guy, and then here there's a 1 over n, plus 1 over n. So we split this 3 into a 2 plus 1, which is some very hard math. Okay? But now we're going to see how this n actually has something to do with the topology of the diagram. So let's see that together. So let's draw what these things mean directly on the diagrams. Okay? So we can just follow what we were doing over here. Right? Whenever you have the pairing, that just means you have this contraction. Right? So let's just do these pairings. So we have a diagram like this. This was the red and yellow. And the green and the blue. Here we had the red and the blue. But this one, you see, now we're a little struggling because I actually can't draw this on the board. This is not going to be what's called a planar diagram. To connect these two, I have to somehow skip over one of them. Right? So maybe kind of draw it like this as if it was coming out of the board. Okay? So another extra ribbon coming out of the board. Okay? And over here, we just have the other guy like this. So let's associate a topology, which is the minimal 2D surface upon which I can draw this graph without any of these edges intersecting themselves. Okay? So this guy, I can draw on a sphere. Right? I can just draw our little just on a sphere. Okay. How do I draw this guy? So this guy, I would actually need to draw it on a torus. Okay? And I would have my little guy like this. And so one of them is going to go around, and the other one will wrap around this way. Okay. And this guy, of course, is the same one, so I can also draw that on a sphere. So somehow it seems that the ones that I can draw on different topology surfaces are actually being counted by this power of n. So now we want to see where that's generally true. Okay. So what we're going to see is that this power of n always keeps track of the genus of the diagram. But again, by genus of the diagram, I mean genus of the surface upon which I can draw this diagram without any self-intersections. Okay, so let's see how that goes. Any questions just about what we did right here? Yeah?
On the previous board, you wrote this ribbon when you were talking about the expectation of Mij MKL.
Yeah.
What does the ribbon itself represent? I mean, why is there another equal sign, for example, on the right? But
sorry. This is just a picture to mean this.
Okay.
This is just a picture that means this.
Okay.
So whenever I had, you see this ribbon, it meant delta AC, delta BB. The same way as what I have over here. So it's just a picture for those things. The Feynman diagrams are always pictures for some equation.
The argument that we can split this expectation value into this smaller expectation value is essentially the same as before, right?
Yes.
It just translates word by word.
It's a generalization of, it's the generalized Wick's theorem. So whenever you have some ensemble of, you have some probability distribution over some set of variables, if in the exponent it's just some quadratic thing, then there's always a form of Wick contractions. Okay, great. So let's try to see that this was not just a fluke. Okay. So what are the powers of n that come with each diagram? So the edges of the diagram, what do those correspond to? Do they come with a particular power of n? Can't be less subtle than this, guys. What's the power of n that you associate to each edge? 1 over n, right? So there's going to be a 1 over n, 1 over n to the number of edges, which I'll denote by e, right? So for each edge, we have this propagator, right? This guy here represented that edge, and it came down to the power of 1 over n. Now let's look at the faces of this diagram. So what are the faces actually corresponding to? Okay, how many faces does this diagram have? Is this a question about issue about terminology, about what a face of a graph means, or? Okay, yeah, that's right. So let's talk about what the. So when we have these ribbons, we have a unique association to a face, which is the interior of one of these index lines. Okay, so we have one face, two face, and then the exterior guy, three faces. Okay, it's easier to see on here. 1, 2, and the outer guy. So there's three faces to this diagram. How many faces to this diagram, actually? We have three faces. One. Okay, so let's try to go through this loop together. So we go 1. Okay, so there's just one single face to this diagram. Okay. Now, what is the overall, what is giving this faces? Okay, so here we see this delta BB, that was this guy, came with a power of n. Okay. The delta DD with a power of n. Okay, so what's happening if I have three faces? Okay, so each face contributes what as a power of n?
Just n. One.
N. So there's an n to the number of faces for each of these diagrams. So that means for each of these diagrams, we have something that looks like n to the minus the number of edges plus the number of faces. Okay. Now I'm going to add and subtract something. Plus the number of vertices minus the number of vertices. And what do you recognize this as? Anyone ever seen this combination together in a graph?
Euler's formula.
That's the Euler characteristic, exactly. So this is n to the 2 minus 2g. Okay, that's this part. And then minus the number of vertices. So how many vertices are there? We draw a vertex for every trace that we draw. Okay? So if we had an expectation value of n traces, or sorry, let's say L traces, we would have L vertices. So instead of calling it L, I'll call it little n. And now you can see these two labels that we saw that are going to pop out in topological recursion, which is this G and this N. Okay? These are going to be the same G and N labels that appear. So what we're going to do is that we can define a notion of a genus to an observable by saying it's the thing that's computed by summing only over diagrams of a particular genus. Okay? So for example, in this case, we could say something like trace m squared, m to the 4 at genus 0 is going to be 2, because there were two such diagrams here. And then trace m to the 4 at genus 1 is just 1. So in particular, what it's saying is that there's going to be a expansion this is an example we just saw. Okay, where we're assigning a notion of genus to an expectation value.
Sorry, can you just remind me what exactly G and N?
Yes, sorry, thank you. So this G is going to be the genus of the surface on which you can draw it. Okay, so let's just double check this formula. So this has genus 0. Right. So a sphere has genus 0, no holes in the sphere. So that is n to the 2 minus 0, n squared minus 1. There's a single power of n cubed over n squared is n. Okay. So this G is going to be precisely the genus of the surface on which this graph can be drawn. It's a really, really beautiful observation by Toft. Okay, so very generally, more questions? Yeah. Keep them coming, What are the questions?
What about the other one at the end? The number of vertices.
That's going to be the number of expectation values of traces we're going to look at. So,
But can we also see it like in this pictorial description somehow?
yes, so here we had trace m to the 4, so we drew one vertex that was 4-valent.
Oh, okay, so the ribbon is like the...
Is the contraction. It's this pairing. The ribbon is the pairing. So let me give you another example. So what would happen if we wanted to draw... so what if okay. We could, for example, look at something like trace m to the 4, trace m squared. So how would I draw this for Feynman diagrams? What would you do?
Well, I guess we put like a cross like this,
Yeah.
and then we do a ribbon.
Yeah, and then one, so that's
One, yeah.
and one vertex that just has 2 legs coming out. So maybe I'll say like 6.
Oh, okay, so it's kind of like fat graphs in a sense.
These are precisely fat graphs.
Okay.
Yeah. So physicists call fat graph ribbon graphs, which is why I just didn't want to call this fat.
Okay.
It's a little rude.
Oh, come on.
Yeah, it's a ribbon. It's a ribbon. Yeah. So ribbon graphs. So they precisely, these matrix integrals, their Feynman diagrams generate ribbon graphs. Okay. And these ribbon graphs, unlike the graphs that we saw before, right, where there was no n, if n is equal to 1, you don't see the difference between these variables, right? But when you keep track of the size of the matrix, you now see that there's different types of contractions that appear. So there's this notion of topology that appears. Okay. Very good. So in general, we can actually always compute, we can expand correlators. So we could look at much more complicated things. Yes. So what this object means is that I put in, instead of just one trace, I might put in multiple traces in that integral, and then I do the integral. And then I only look at the connected Feynman diagrams. Okay? So meaning that all the vertices are connected to one another. That's one way to define what I mean by connected. And then this guy will always have some expansion by this argument we just saw, in terms of a genus expansion. So there's going to be a 1 over n expansion of all these type of observables, and they always have this topological expansion. And by that, I can just define this as the sum over all Feynman diagrams of a particular genus. So now you had a question.
Do you want to keep, or do we want to keep track of the n's as well in the things you wrote on the line?
So that's why I put the n here, and then this just denotes the coefficient. Okay.
Can you make sense of this if 2 minus 2g minus n is non-negative? Because, for instance, for the modular space of curves, you need it to be negative as a stability condition.
Yes. So there's, in fact, we did it here, right? So
it's guaranteed to be negative.
No, it's not. There's no stability condition in that sense, yeah. And in particular, in fact, the input of topological recursion in some sense is the unstable data. This is not important for just to answer the question. It's going to be basically a cylinder and a disk. So it has negative and 0 Euler characters.
Sorry, can you explain again what is the little n?
The little n is the number of vertices of the diagram, and that's the number of traces that I insert here. Maybe we should do an example. Would it be helpful to see maybe like a 2? I tried answering that question earlier where we had trace m to the 4 and trace m to the 6. We draw 2 vertices, and then you would do all the contractions. And connected means that this vertex has at least one leg that goes to the other vertex.
Just a quick question. What's the limit of the sum? It goes from 0 to, I can't read the...
Well, so that actually depends. So It can be infinite, but in this case, it usually truncates. There's some maximum number of genus. There's a maximal genus, right? So like here we had 2n plus 1 over n, but we didn't have like 1 over n to the 7 or something, right? So usually it truncates and... Okay, very good.
Okay. Question.
Yep.
So in particular, the middle graph has the different topology there.
Yes.
So if you're following the logic along of multiplying graphs, in a sense, it's just multiplying numbers.
Yes.
The sense of connected is sort of different if you're in this topologically non-trivial thing. So for example, you could link these two. You could link two of these middle graphs together on the torus.
Oh, but that would compute something different, of course, right? Like each one of these graphs is one particular contraction here. So there's no sense in which I have some tie between these things, right? These are really plus signs. I'm summing over all pairings.
But just to say the logic of disconnected versus connected is sort of disappeared a little bit here?
There's no sense in which you'd have a genus 1 guy that's connected to like a genus 3 guy. Like if it's connected, it just means that there's one surface upon which you could draw it, and then you ask about the genus of that surface. Yeah. Yeah.
In the small example you drew, you specified the genus.
Yeah.
Including the one that we worked in, you didn't.
Right. So here we took trace m to the 4. So let's just show this again. So we have right now. So we took trace m to the 4. Okay. So there's going to be a sum over the genus n to the 2 minus 2g. N is equal to 1 here, so minus 1. Times what I mean by trace m to the 4 at genus g. Okay. So that was this leading an n piece here. Right? Genus 0, so that's 2 minus 1. It's 1.
And these factors are always integers, right? Because you have this combinatorial interpretation.
Yes, so, right. So these guys are actually, in the Gaussian ensemble, are integers. But if I now have some interaction, they'll be functions of the coupling. I'll tell you some cool fact about that later. It turns out there's a very nice connection to string theory that arises, that this is partly what I work on, is understanding how you turn a matrix integral into a string theory. This was kind of the old dream of 't Hooft. And we can write all of these guys as particular integrals over the moduli space of Riemann surfaces. And it's a very complicated integral, but it's very surprising that it spits out integers. And you wouldn't know that unless you knew that it was dual to some matrix integral. Not important for everyone. Good. So this was one of the main things I wanted to do. Now what we're going to do is, so you've seen the Feynman diagrams, you've seen now the matrix generalization, you've seen the connections topology. Now what we're going to do is to do something like the Schwinger-Dyson equation. Okay? I think we'll do that, and then we'll talk about interactions in Feynman diagrams a little more. Maybe I'll just do one more example for you guys, just so that we have one more. So, let's ask about, so trace m to the 2k of genus 0. Okay, so again, this Gaussian matrix integral. So, can you see how this becomes a hard problem quickly? Right? So what you need to do is you need to draw a k-prong vertex. Okay, something like this. This would have 2k legs. And then you need to look at all just the contractions where there's no there's no, none of these contractions kind of cross. So these are what are called pedal diagrams. And there's actually a way of counting them. Okay. And we're going to see that the number of these diagrams are actually precisely the Catalan numbers. Okay. 1 over k plus 1, 2k over k. But that's very hard to see combinatorially, not totally trivial, right? So we're actually going to derive by the end of the class, using something like a Schwinger-Dyson equation, how we find trace m to the 2k very generally. So we're going to solve this combinatorics problem by using some sort of recurrence relation. Very good. But maybe we can do just one of them together for fun, just to get you a little more. So let's take k equals to 3. This is trace m to the 6. So we can draw these guys. Okay. So how many such diagrams? And we're only drawing the planar ones, right? Do I need to draw? I was figuring out. Okay. Now you guys got to help me find all the planar ones. Okay, so let's try to do this together. Okay, so we can do one here like this. Okay. Then these. Okay, so that one's not too bad. Now, this guy, can it contract with here? Why?
The other one can't cross.
Exactly, so this one would cross, right? So it can't go here, so it at least has to go to here. Okay, this can come, this one. Okay. Try another one. So this one, this we've done.
There's another possibility.
Yeah. Yeah. So this we've done. This is not okay. This we just did. How about this guy?
That's a odd number.
Right. So this one, okay, is that. Now how about here? So we could bring these guys together. What's another possible pair?
Polar opposites.
This one with this one? Yeah, exactly. Okay, there we go. Okay, what's missing?
First one, but different connection at the bottom.
Okay, so like over here.
This
we already have?
It's the same as on the top right.
It's probably on the same as on the top right. Really? Yeah. Missing.
Why the same? I mean, it's rotated, but does that mean it's the same?
These are not the same diagrams.
The top left and the middle left are also rotated with each other.
With the rotation, you can just take this one big ribbon and pull it around.
This one is not the same as.
The second one. It's the same as the
that
second
one is. Yeah,
Exactly the same as
I agree. Yeah, that one we have already.
You're missing the one where you connect the two things on the top.
Where I connect these guys and this. Good. Anything else? It's a trick question. There's only 5. So there's only 5. Okay. So in particular here for k equals to 3, if you can check fits the Catalan over there. Okay, very good. But you can see how this becomes complicated quickly, right? So we don't want to just keep drawing Feynman diagrams. The reason we really needed this Feynman diagrams was to establish what we mean by this, was to see some sort of topology in the large M expansion. Okay, so now let's move on, and let's move on to basically this matrix Schwinger-Dyson equation. And then if we have time, we'll come back to some more Feynman diagrams in perturbation theory. But I think let's just see first how much time we got. Okay. sorry, can you remind me when we stop?
At 7:30. No, at 7:30.
7:30. Okay, so we got another hour. Okay, so actually then I think we have a little time for a few things to say about the matrix integral. So now what I want to do is to upgrade our little quartic integral to a quartic matrix integral, and now discuss two types of expansion. So there's going to be the expansion in n, but there's also still going to be the expansion in this coupling constant in front of the coordinates. Okay, so let's do that now. So we'll do perturbation theory of the matrix model. We're really just trying to kind of mirror the steps that we did in the first part of the lecture, but now with the 1 over n expansion on top of it. Okay. So how do we generalize our little example over here? Gx to the 4. So well, the way we're going to generalize this is as dm e to the minus, here we're going to do something a little different. Put this n out here. Our lambda. Trace m to the 4. So this is actually what we call, in physics, the 't Hooft coupling. So this is going to be kept fixed in the large n limit. So there's an extra factor of n out here. Okay, I could say a few more things for physicists. For example, if this was something like, how many physicists are there in? If this was something like a gauge theory, this factor actually would be g squared times n. So it wouldn't actually be the Yang-Mills coupling. It would be a different parameter that you're keeping fixed, which is g squared n. So the Yang-Mills coupling is going to 0, n is going to infinity, and you're keeping this lambda fixed. For the mathematicians, you don't need to care. Okay. So if you want, the only statement is that that's what we're going to keep fixed with that n out in front. Okay, very good. So how would we compute now this z? It depends on two things, right? It depends on this lambda, but it also depends on n. Okay. So we could do perturbation theory in exactly the same type of way, right? Where we expand e to the lambda trace m to the 4, and now we compute expectation values with powers of trace m to the 4. But what's going to happen? So actually, I'm going to cheat ever so slightly. We're going to do an expansion in log z. It's just going to keep track of some connected diagrams. Is it helpful for me to write this out, or do you guys remember this from the first part of the lecture? Right. I'm just doing a Taylor expansion of the exponential, nothing fancy. So you would be computing something like lambda over 4 to the little n, trace m to the 4 to the n, right? So those would be the various terms with a 1 over n factorial. So this connected guy now has an expansion in 1 over n, right, as we just saw over here. So it means that we can do we have a double expansion now. So we have an expansion in this lambda, but at each order in lambda, this guy has itself an expansion in n. So there's a double expansion with g and with n. Something with lambda to the n with some coefficients that will depend on g and n. So these coefficients are just the number of Feynman diagrams at a given genus with n vertices, n quartic vertices, right? This is the number of Feynman diagrams, genus G, and n quartic vertices. So why are the vertices all quartic right now?
Trace m to the 4.
Because this is this quartic down here, right? Trace m to the 4. So if I had trace m to the 6, there would be a bunch of 6-valent vertices over here. Right? So if we expand this, we just compute these expectation values. By something I didn't really explain to you, by taking the log, we just look at connected diagrams. And connected diagrams have this expansion.
These are two relations here on the left and the right, or is it one big one?
Sorry, so here I was just saying, at order lambda to the n, this is what we're computing.
So the CGN is the thing on the right, essentially.
So the CGN is basically this.
Okay,
Exactly.
perfect. At a fixed genus.
At a fixed genus. So in other words, this is equal to trace m to the 4 to the n at genus G. Right. So earlier, for example, we found trace m to the 4 at n equals to 1 was just 2 for genus 0 and 1 for genus 1. So there's a double expansion that's going on with n and lambda. Now here's the really beautiful thing. So what we can do is we can, for example, we can do the sum over lambda first. So we're going to imagine that we first do the sum over lambda. So there's an n to the 2 minus 2g. Well, actually, there's an n to the n here that comes from here. Sorry, so there's an n lambda to the n. Okay. So if I do this guy first, this actually is going to define some function of lambda at each genus. So the number of diagrams, which comes with the power of lambda for the vertices, and I sum over all diagrams of a fixed genus, but with different number of vertices. So this is some Taylor expansion of some function, fg of lambda.
Are we certain that it actually is a well-defined function? Because this is just a form of power series at this point.
Yes. So here's the beautiful thing. This is actually a convergent expansion.
So where did the n to the n?
It's because you have n times lambda.
I mean, like in passing from first line to the second, like there is.
You forgot it.
Like the big n to the power of.
So that's just because the connected correlator has this expansion over here.
No, I mean, when you move from there to.
The connected correlator has this expansion over here. But here we're actually expanding with n times lambda. So there's an n lambda to the n. So there's a n to the little n that cancels this one.
Yeah, but you should write it explicitly, because right now you just have lambda to the
Put it
n.
here. So the CGN is with this n over here.
Okay.
Okay. Did that answer your question? There's this guy, and it cancels with n, this guy over here.
I mean, just looking at the equality there.
Because you kept the lambda. That's his
Okay,
objective.
I understand. Let's put n lambda. That'll make a. Okay, so there's a n lambda over n factorial 4 to the n. This is just the terms in the series. And this will define the CGN as just the connected. So the really beautiful thing is that this is actually a convergent expansion. Let's put out some ideas why you think this might be a convergent expansion. What does it tell you about the number of diagrams? So earlier when we saw this asymptotic expansion, what was the problem?
All of the diagrams that in this case would have different topologies. In the previous example, they all have the same topology, so they all add up. So it means that when you go for like further away, for n bigger, it just keeps exploding and it explodes like linearly. And in this case, because we can distinguish between different types of topologies, I guess it doesn't explode.
Very good. That's exactly the reason. So let me just kind of rephrase what you said. what we were seeing before, when we had this asymptotic expansion, is that the coefficients in the expansion were getting big very quickly, right? So they were dominating the 1 over n, 1 over little n factorial that came from the Taylor expansion. Okay? There were just too many diagrams, and that's why the sum in that Taylor series didn't converge. Okay? Because the coefficients in the expansion are precisely the number of diagrams. So what was happening is that there's too many Feynman diagrams, and that's also why your job gets very complicated when you actually try to do classic Feynman diagrams. When people do this in QFT, they have computer programs that automate this, and they do, 9 million Feynman diagrams. It's really, really impressive, okay? But the number of diagrams grows very, very quickly. And it grows basically a little too fast and factorially, and that suppresses the 1 over n factorial in a Taylor expansion. What's happening here is that when we first say we're going to fix the power of n, we're only going to look at diagrams of a fixed genus. Okay? And the number of diagrams at fixed genus grows much slower. Okay? And it doesn't grow factorially. That's the important part. That's what allows this to actually be a convergent expansion. Is that just the number of diagrams is less than before, right? So okay. Here they're doing first order perturbation theory, so it wasn't great to see. But before we had 3 diagrams, and now we had, at genus 0, only 2 diagrams, genus 1, 1 diagram. As you can see, if I fix the genus, say at genus 0, I had less diagrams. Right? So what the 1 over n expansion does is that it filtrates, in some sense, your expansion by topology, but then each one of these becomes convergent. So that's a really, really beautiful fact. And this was, so one of the things we're going to be trying to do is to be computing things like this as a full function of lambda. We're going to use the Schwinger-Dyson equations to do that. So we're going to see that if we, for example, take the strict n to infinity, we look at genus 0, then we can actually compute things as full function. Okay, very good. Any questions about that?
Why do you need to send n to infinity?
So at n strictly to infinity, then I suppress everything else. So in n equals infinity, when n is very large, I only need the planar diagrams, the genus 0 diagrams.
Right.
But of course, if you keep 1 over n corrections, right, further power corrections, then you look at things with increasingly complicated topology, higher genus. Yeah. Okay, very good. That's also why sometimes you might see this called as the planar limit. The large n limit is sometimes called as planar limit. Okay, great. So here you saw the upgrade of this perturbation theory. Now what we want to do is we want to try to come up with non-perturbative ways of doing this, right? So again, this is a very complicated object to actually compute in practice, right? So we need to find some different ways other than trying to find all the graphs, right? So we're going to come up with an equivalent now of a Schwinger-Dyson equation. We're going to get to the spectral curve of the matrix model by the end of this. Any more questions? What are we going to do? So we're going to try to mimic exactly what we did with our little baby example of Roche. So it's going to start with 0 equals the integral of a total derivative with respect to Mij. And now here what I'm going to pick, maybe I'll call this AB. So this is m to the k. Ij. Matrix integral Schwinger-Dyson equations. Three, four. So, very good. Okay, so this is where we're going to start. Okay, so same starting point. And now what we have to do is we have to do the same thing. So we take derivatives, either acts on here, or it acts on trace via them. Okay, on the exponential. So, how are we going to do this? So, let's do this together slowly. And some part I've also put as exercises for you. Okay. So is it clear what this means? This means take this matrix, multiply it k times, so to the kth power, and it's the ijth entry. And I'm going to take a derivative with respect to the ijth entry of the matrix, and then I'm going to sum over I and j. That's what this equation means. Okay? Good. So the first thing we're going to do is that this can act on that. So we need to say that this, so 0 is either the expectation value, ddmij, so that's when it acts here, and then it can act over here. So it brings down a power of minus n m to the k ij, so times that, times this vm. So this is equal to 0. Okay. So now what we need to do is we need to understand how to take this derivative. So we're going to do a little simple one. I'm going to first just tell you the answer, and then we're going to just kind of check that out on a little simple case, and that'll be left as an exercise. So one of the exercises for you is the following. Check this for trace m cubed. The k equals to 3. But I want you to prove this in your glorious free time. Okay? And it's not a hard proof. Okay? And you're going to see probably just from the k equals to 3 case how this happens. But you can leave that as an exercise for you. And it's kind of quite remarkable, right? It's taking the single matrix and it's splitting it into two traces. And we'll see geometrically what that means in this topological recursion business later. So let's do this. So we can just do a k equals to 3 example. Okay. So there we take ddmij of mia, nab, and bj. So this can act in 3 different spots. So you can tell physicists, they just love to compute things sometimes. Right? It's just, so what are we going to use? We're going to use that d, mab, dmij. This is 0 unless you're taking a derivative with respect to the right entry, right? So this is delta ai, delta bj.
So now we don't take this metric, or?
It's Hermitian. So the less pedagogical way is to split it into the real and imaginary part, and you take these derivatives, but it's the same as saying z and z bar are independent when you take derivatives. It's the same thing. Yeah. Okay, so we take the first guy, so we get a delta I, delta ja, NAB, j. Okay, now it can act on the second one. Delta IA. So let's just check that this, I'm not lying to you. Okay, so this should be the sum r from 0 to 2. Okay, trace m to the 2 minus r, trace m to the r. Okay, so what is this? So this is n, right? Which is trace of m to the 0. Okay, and then this guy is MAB and BA, So this is trace m squared. Okay, so that's the r equals to 0 term over here. Okay, and you can see how the rest of the terms work out. Right? We don't need to deliver. So if you want, in your free time, you can just write this out for a generic k. You act on the derivatives, and it always gives you this factor. Okay, that's a very cute idea. Okay, good. So far so good. So we have this one. Now how about a polynomial? So what happens if we just take a derivative with respect to a trace? So first of all, does anyone know the answer? What happens if I, for example, take this?
The trace is linear.
Yeah.
So you can just bring it in.
Yeah.
You already have the formula, so you can just contract it.
So this, let me just say, this is this squared. Right. So I urge you to also check this, another exercise. If you want, we could go through exactly the same type of manipulations right here. But what you would see is that just because of the index structure, it's always a single power of the matrix. Okay, so d mij trace m to the L is L. It's basically like how you would think of for a polynomial works.
Yeah.
Actually, did we make sure to press the?
Yeah.
It's probably a little late now, actually. That was Elise's karma.
It should be an L minus 1 in the exercise.
L minus 1, yeah, so thanks. Yeah. Okay, so let's now put this all together. Okay, so we have 0 is equal to this first piece from what we just did over here. So it's going to be r equals to 0, k minus 1, expectation value trace. Okay, minus n trace. So m to the k times v prime of n as a matrix. Any questions? Okay. So now we're going to do something cute, which is that we're going to actually try to not look at a fixed value of k. So we want to introduce what's called the resolvent. Okay? And the resolvent is going to end up being one of the variables of the spectral curve. So that's why it's going to be important. So now, the resolvent. And this is also where x of the spectral curve is. I'm going to define r of x. Is the blue readable, or is that also?
No.
So other than white, what's the most readable?
Red.
Red? Red and green? Yeah. On the Christmas cards. Okay. So I'm going to first write a formal definition of what I mean here. Okay. Trace 1 over x minus m. So this really means x times the identity minus m. Okay. And one, the best way to probably think about it is really, what I mean by this is a geometric series. So. That's what I mean by this. So what are we going to do? We're going to start with our Schwinger-Dyson equation up here. Okay. Let's see if you want here. And I'm now going to multiply this by 1 over x to the k plus 1. So I'm going to multiply this whole equation. And then I'm now going to sum over k. Okay. Sum over k from 0 to infinity. and that's still 0. Okay, so what happens now? So note that actually this is going to become actually 2 resolvents. Okay, so let's see that really quickly. So we have a sum of, so let me try to distribute this over here. So this one's easy. This is just x to the k plus 1, so that's going to give us a resolvent. And here I'm going to split it as x to the r plus 1. So note that I didn't do anything. Huh? This still just sums up to x to the k plus 1. But now, here, okay, my sum was bounded up to k minus 1, but now I'm summing over all k. So that means that these now just become 2 independent sums. Okay. Let's say over r and s. So I have, let me call this s, this m to the s. Minus n trace v prime of x, oh sorry, v prime of m. Okay. So note that again, this is also just trace 1 of x minus m. Okay. So we just multiplied by this x, we do the sum. This becomes 2 independent sums, right? This condition doesn't really matter anymore. And we get 2 times the results. Very close to the spectral curve. Okay. So we have 0 is equal to trace, I'll call this r of x, trace r of x. Now I'm going to split that into a connected and disconnected piece. Okay? So there's going to be a trace r of x squared plus trace r of x, trace r of x.
But if you define r of x to already include the trace. You define r of x to already include the trace.
Oh, did I put the trace? So let's not put the trace here. Okay, so we took this 2-point function of resolvents, and either that's a disconnected piece, so it's a product of 2 1-points, or it's a connected 2-point function. Okay, this is just saying AB is A, B plus AB connected. Is this part confusing? This is the definition of the connected piece if I subtract that off. This is just the definition. Yeah, so we're not done. We're not done, right? So we've got minus n trace, okay? And here I'm going to do something. I'm going to add and subtract 2 terms. We're almost done. And we'll continue around that board. This is the long derivation. Sometimes you just gotta. So we've got trace 1 over x minus m, all of this squared, plus connected. So I'm going between r of x and not. Just feel that confused you guys. Okay. Now this guy just comes out. So minus n v prime of x over plus n okay. started with this sort of trivial identity. Now we just kind of massaged it, and we're getting some sort of, we'll see a recursion relation.
How did we pull v prime of x outside? There's not, we haven't made any restrictions on v. There's no guarantee that v prime of x is not self matrix.
So v prime of x is just a function. It's just a number times the matrix 1.
But v prime is, sorry, but v is a matrix taking, sorry, is a function taking a matrix input.
Yeah, so we're going to take v into some simple polynomial. So like,
okay, then when we restricted that is fine. Okay.
Yeah. So we had something like this, right? Earlier.
No, that's fine, but until now we had not restricted it at all.
Yeah, no. So we're taking something very simple like our quartic guy.
That's fine then.
Great. Okay, very good. So in particular, actually, this is just some polynomial in x of degree 2 times less than v. So it's v prime, but then you're also dividing by this x minus m, so it's degree v prime prime. So that's some polynomial. Okay, very good. So far, this doesn't look too useful. But now, we haven't used the 1 over n expansion yet, right? That's what's been missing. That's the real new ingredient. We haven't used ygen. So now we want to keep all the terms that are the same order in n. We want to filter this equation by n. So remember that this guy has an expansion in g, n to the 2 minus 2g minus 1. So we've taken each one and we've just done the expansion in 1 over n that we did earlier. So little n is equal to 1. That's this first term. And this guy is connected, right? So this guy starts in h, n to the 2 minus 2h. And what is n? Minus 2. We've got the same thing over here, but now with an extra power of n.
So you mean n to the power 2 minus 2g?
I meant h. I put h here.
Oh, okay.
H. And then we're going to keep all the things that are the same power of n. So I'm just going to define this as some polynomial. Okay. N v prime of x almost done, just the last guy. That's n. Okay, so all we did is we took these things and we just used their 1 over n expansion. And now what we want to do is that we want to look at the terms that are the same order in n and keep only those. Right? So this gives us a whole series of equations that are labeled by the coefficient of n. That's the main difference from what we had earlier. And now we're going to see different topologies are going to be mixing, and we're going to be leading to a topological recursion relation, which we will probably only really get to in full glory in the next lecture. But we'll at least get to the spectral curve. Okay, very good. So what is the leading piece here? Okay, so let me write this way. G is a n, so n squared minus, so I'm going to call it h and g. Sorry. Let me get this right. So we're going to keep it the same power here. G. And then we're going to split this up to G. So we have two sums that go up to infinity, but I can always do it this way, right? So I write it in terms of g and g minus h, where h goes up to g. So that's going to be the first one. And this one, I'm going to, so this has a leading, this is 2 minus 2 h plus 1. Right, so I want to define a g which is h plus 1. So h is g minus 1. So sum, all the same way as g. So this, of course, only makes sense if g is 1 or greater. Okay, we're losing people. Let's slow down. So what's? Are we good? Are we good up to here? This is always when you do algebra. There's some algebra you got to take. The others, I left those exercises. So this is the one piece of algebra we're going to do. Let's debug where we're stuck. So were we happy? Were we happy with this? Are there questions about getting up to this equation? No? Here we're good? Okay. Are we happy with this equation? Yeah. So now it's just about the 1 over n expansion. So remember that we said that a correlator, okay, can be expanded in powers of 1 over n, just like we did earlier, with 2 minus 2g minus the number of traces inside. So that's all I did over here. And I did that for each of these terms. Now what we're trying to ask is, let's say I want to isolate a particular coefficient. Like what's the coefficient of n to the 18? N to the minus 1 over 18. N to the minus 18. Okay. There's going to be one particular term in that equation, right? I can look at all the terms in that equation. So what we're trying to do is we're just trying to write this as a particular power of n and ask what are the coefficients of that equation. That's all we're doing. So this is, for example, just a clever rewrite, right? Because, for example, here you would have g and g prime, right? Because it's a square. So, you know, maybe once g is 0 and g prime is 1, maybe once g is 1 and g prime is 0. Okay, so you could have cross term. This is a way to just try to, you know, figure out what's a particular, so the particular term in this sum of a given power of n is going to be this. Okay. So same thing here, right? We now relabeled h, so we want to have this as g. So h plus 1 is g, so h is g. Okay, very good. So, sorry, this is a little messy. So this power of n cancels this minus 1, so that already starts with n to the 2 minus 2g, so that's good. And this polynomial over here, same thing, so p of x. Okay. So this is our equation at a fixed power at n. It's that this whole thing here has to vanish. At each power at n, you have this being 0. Okay.
How did you cancel the first n to the minus 1 there? Like in the very first thing, we have n to the minus 1.
Yeah.
How did that disappear?
So we have n squared squared, so there's an n to the 4. Okay. Here you have an n minus 1 squared, so there's an n to the minus 2. 4 minus 2 is 2.
Thank you.
It's always nice when these things work out. Yes, indeed. Okay, so now let's just write this down, for example, at genus 0. So here we're getting to the spectral curve. So take genus 0. That's one of the terms we can consider. Okay. So in particular, here then there's no sum. This just becomes trace 1 over x minus m g equals to 0 squared at h. Okay. Well, what about this term? Is that term there? It's not there. Another way we could have said it is that the connected piece, right? If you just were drawing Feynman diagrams, each one would already have an order n squared piece. Right? There would be some planar diagram. So if you square it, it starts with n to the 4. Whereas here, if this is connected, the maximal topology is genus 0, so it's n squared. So that means that large n, this is suppressed relative to that. And that's why we're not seeing it here. Genus 0 is the large n limit. So we're neglecting this piece here. And this is really where the magic happens. So v prime of x, trace of x minus m genus 0, plus some polynomial 0. Now here's the really amazing thing, is that now this is actually just an algebraic equation for this resultant. Okay? So in fact, we're going to define this now in some other color. We're going to define this as y. So we now get y squared minus v prime of x, y, plus some polynomial of x is 0. It's an algebraic equation. This is what's going to define the spectral curve of the matrix model. So this equation, we're going to think of x and y as complex variables. Okay. So if I have two complex variables and one complex relation, how many independent variables do I have?
Four.
How many independent complex variables do I have? So I have two complex variables, x and y, subject to this equation. I have one left thing, right? So I have a complex curve. I have a one-dimensional manifold, which is the locus of this equation in C2. Okay. So the locus of the complex xy plane, so C2, this is what we're calling the spectral curve of this matrix model. It's a nice geometric shape that's carved out in C2. Okay, so two real dimensional space. What's absolutely incredible is that this equation is going to be enough to compute all of the connected correlation functions to all orders in 1 over n. This one starting point. Okay? So we're going to basically bootstrap our way from this little, this is why I made you suffer. It was worth it. Okay? Other things it's not worth. Those things aren't worth suffering for, but this is worth it. Okay? There's some sense of complex geometry that is coming out of the matrix integral, and it's precisely via this Schwinger-Dyson type of equation. Now, I want to illustrate the power of this equation for you by finding those same Catalan numbers that already just drawing the 5 diagrams got us a little tricked up. Okay? So let's consider this for the Gaussian example, and we're going to see how we're going to be able to compute trace of m to the 2k directly from this.
Before we proceed, just one quick comment.
Yeah.
So,
when we comments, not questions. You know,
no, it's a question that means comment that implies a question. So, for the actual geometric series to converge, we require that x lies outside the spectrum of m.
Yes. So here
but we're integrating over m. And then we have x as a free variable, so it's kind of messy.
So it turns out that, yeah, so this is an expansion around x equals to infinity.
Yeah.
And in the large n limit, the eigenvalues of a random matrix are actually concentrated in a small area. So they actually don't overlap.
Okay, perfect. Fine, if that's the case.
Yeah. That was a great question. Okay, very good. So now what I want to do is to take this spectral curve and show you the power of it. But before that, we'll answer this question.
Sorry, does this have anything to do with the Stieltjes transform of? It remembers me of that the eigenvalue. The semicircle law It's still just transform satisfies an equation of
That's correct. That's precisely what this is.
This is the unitary ensemble.
Hmm?
I mean, it is a unitary ensemble.
Yeah, this is GUE. Yeah. Okay, very good. So, let's do that. So let's go back to our little spectral curve, and then I'll give you an exercise for the quartet. So let's, so specialize to v of x is x squared over 2, which is what we started out with, right? A little matrix into that. And now let's see what this looks like, okay? So we have y squared minus v prime of x, that's just x. Okay. And now what is this polynomial? So it's the expectation value of trace v prime of x, x minus m, over x minus m. So this is actually just the identity. Okay. And with this factor of n over here, so this is just going to be 1. So this p of x for us is just going to be equal to 1. For this particular choice. Okay. This polynomial was defined as trace of v prime of x minus v prime of m over x minus m. So for the Gaussian, this is very simple. Okay.
Okay. The trace of identity is like the dimensions, big N.
That would be big N, but we actually kept track of that over here. So when we did an expansion in N, we kept track. There's an N here as well. Okay. So let's look at this point. So later we'll talk about what's called a uniformization of a curve. Right? So if we have x and y and they're both subject to one constraint, there's one free complex variable, we say. And often we write them both in terms of z. So often spectral curves are actually a pair written in terms of a uniformizing coordinate. It's called z. This one is actually quite easy to write. Okay? So here we're going to take this to be, don't even need to do that right now. So let's solve for y in terms of x. Right? So just remember y is equal to trace 1 over x minus m at genus 0. Okay? So let's solve this equation. So this is y is equal to, this is just a, okay, so minus b, x plus minus b squared. 4 times a times c. Looks like this. Okay. And in particular, I'm going to now bring out x over here. I'm just going to write this as x over 2, 1. So how do we fix the sign of the square root?
Y has to be positive, right? Because we are counting things.
Why is the sum? I mean, yeah, like, that's true. What do you know about the asymptotics at large x?
Trace of 1 over x, so we don't care about it. 1 over x is a constant, so we just take the trace.
So the first term is that y of x has to go as 1 over x plus higher order. Okay? That just comes from this definition. Right? The first term. So the k equals to 0 is trace of the identity, but that factor of n is already included in our 1 over n expansion over there. Okay, so this looks like 1 over x plus other stuff. So what does that tell you over here? we need the minus sign, right? So that at large x, this will look like square root of x squared. That'll cancel this guy. So we have a minus sign. Okay, so we get this minus x squared. Okay. So far this seems not so nice. But now, if you want, you can just put this in Mathematica, or maybe people who've worked along with combinatorics and generating functions might recognize this function. I'm not expecting you to. Okay. But now we can expand this in large X. Okay. So if we expand this at large X, this looks like precisely the generating function of the Catalan numbers. Okay. So these are what are called Catalan numbers here. Okay. So if we now compare the two sides, what does that tell you? It tells you that just this very simple structural curve equation already did all the Wick contraction combinatorics for you. It tells you that trace m to the 2k at genus 0 is equal to 1 over k plus 1, 2k over k. Okay. So we did trace m to the 6 earlier and tried to count the petals. This solves all the petal counting problem directly for you. By starting with this Schwinger-Dyson type of equation. So in the last 10 minutes, I'm just going to pose you an exercise, and I'll let you solve this at home. Is that you can see that this equation didn't really depend on what potential we chose. So it wasn't actually specific to the Gaussian or anything like that. We can do this now as a full function of this lambda. So what I want you to do at home is to compute this guy as a full power series in lambda. Okay? You're going to give it as an entire function of lambda, and you can then Taylor expand it. And then you can check, if you really, really have nothing else to do, that those are equal to the number of diagrams. And this is actually a very famous paper called Planar Diagrams by ETH Zurich and Parisi and Prezin, I think, yeah, which did exactly this. Okay, so they use different methods, but that was one of their beautiful first results. Okay. So I'm going to leave this as an exercise to you now. Exercise, but I'll give you some hints, huh? So, okay, so redo, find y of x, let's trace m to the 2k, 0, in the quartic integral, meaning as a function of lambda. X and this lambda parameter. So I'll give you a few hints. So we can always actually write this equation in this way. So y squared minus v prime of x plus this polynomial is 0. So y always looks like now, what's the complication relative to the Gaussian? What was nice about the Gaussian? Yes.
Doesn't.
I think in the power series you wrote on the last board, you need 1 over x to the 2k plus 1.
Yes, that's right. Thank you. Yeah, it's even. But in general, this polynomial p of x, we don't actually know what it is, right? This polynomial is part of the things that we don't know, right? It's asking about the expectation value of a single trace thing, which we. But actually, you have all the data you need if you make a particular type of assumption called the one-cut assumption. And if you want, that says that this can also be written in the following way. So this is what's called the one-cut assumption. And I'll say why it's called this. But so it can be written as some polynomial like this. Seems sort of surprising probably to you, and it should. I'll just tell you first of all. So this actually is a polynomial of degree v prime prime. So it has, if this was a quartic matrix integral, it goes up to x squared. And there are 3 unknown coefficients, a0, a1, a2. Okay. Let me just tell you that the asymptotics that y goes as 1 over x, this order 1 over x squared, is actually enough to fix all of these coefficients for you. So what you should do is you should take the potential that we had. Okay, so this was v of x is x squared over 2 plus lambda over 4, x to the 4. Okay, you put it in here. Then you ask for these asymptotics. You're going to solve for these coefficients. Okay, and you'll actually have the full function of y. Okay. Once you have that, you can then compute trace of m to the 2k by this expansion over here. But this is going to be something that will be a full function of lambda. Okay? You're going to find that all of these coefficients and this u over here are determined as a function of lambda. So what those are is that they resummed infinitely many Feynman diagrams. Right? What you've done is this allows you to compute trace m to the 2k in this quartic. 0, and of course, okay. So in general, this would be a very hard thing for us to compute, right? This would be Feynman diagrams with n quartic vertices, 1 vertex that has 2k legs coming out. We have to compute all the contractions. Very hard job. So you would do that for each of these guys. You would multiply it by lambda. You would resum it. And you would get the full answer as a function of lambda. Right? This would be a very hard combinatorics problem. This would be infinitely many Feynman diagrams to compute. Instead, what this type of job is going to do is it's just going to find the solution very simply. You just need to fix these 3 coefficients as a full function of lambda. You've resummed all the planar diagrams. And what we're going to see is that what Eynard or Ranton topological recursion does is that once you have this data, you can then find this at genus 1, at genus 2, at genus 3, okay, higher and higher orders in 1 over n. So just by knowing the planar one-point function, you sort of bootstrap yourself up and find all the other information. It's really, really amazing. Okay. So we're going to see a more complicated recursion relation that arises by very similar manipulations, which we probably won't do in person. Okay. But I'll at least tell you where it comes from, and I'll tell you the equation, and I'll tell you finally what Eynard or Ranton topological recursion looks like. And then, okay, any questions about this?
Is there any reason you would expect to see the Catalan numbers come out? Like, is there some connection with non-crossing pair productions or something like that?
Yeah, the non-crossing pair productions were precisely those pedal diagrams that we were drawing together.
Are you going to say something more on this one-cut assumption?
All right, I can. Okay, 5 minutes.
You have time. You have time.
Okay, so what do I want to say? I can maybe say a quick thing. I'm probably going to get a few factors wrong, but I'll say a few things. So, okay. So I didn't introduce any of this today, so you can also totally tune out. But for those who are interested, when you study an ensemble of matrices like we've been having here, right? So we integrate over all these matrices with some probability distribution. When you pull out this matrix and you diagonalize it, you can make a histogram of its eigenvalues. And if you keep doing this for many, many pulls of the matrix, you start finding something like this. So this is what do we want to call eigenvalues? It's not lambda, it's not this quartic coupling. S are the eigenvalues. You start finding something that looks like this. So this is if you kind of make a histogram of the eigenvalues where you pull all the entries, say, just as Gaussian entries. So this was, for example, for
what's the y-axis here?
Yeah, so this is just basically some density of eigenvalues. So we'll call this rho of S. So if there are n eigenvalues, it's the number in each bin divided by n. And it's symmetric. So this is S equals to 0. Okay. This is really the axis. Okay. Now, if you do a Monte Carlo simulation, where we now add, for example, say lambda here, you'll find that essentially you get a similar type of distribution, but it kind of, depending on the power of lambda, it creates some bumps. If I tune this power of lambda enough, at some point, actually you get something that's disconnected.
But it's always symmetric. But it's always symmetric.
It's always symmetric. Well, it actually doesn't have to be symmetric. So the centers are, but actually you could have different numbers in each side. Yeah. When the eigenvalue distribution is connected, we call this one cut because it has support on one interval. And I'll explain what this has to do with cuts. Okay. In this, we call this a two-cut solution. This is disconnected. Now, why am I telling you anything about eigenvalues when we just talked about the resolvent? Okay. And it basically comes from the following identity. I'm going to get this wrong with some signs. But there's some 2 pi's and some i's and some delta of x over here. Okay. So the point actually is that if we trace 1 over x minus m, and we now try to write this in terms of the eigenvalues of this matrix, this looks like x minus si. Okay. I diagonalize the matrix S. So one thing you can do is you can actually now try to, compute. I can look at x a little above and below the real axis. So I'm now looking in this x. Well, it's too much to explain at one time. Okay. But roughly, this is trying to answer your question about the Stills transform. So if I look at the discontinuity of y, so this y has a branch cut because of this square root. That ends up being precisely where there's an eigenvalue distribution. So imagine all these eigenvalues are here. Okay. And then I look a little below and a little above. So in n equals infinity limit, there's sort of infinitely many eigenvalues, and they're always in some range. You can even just find numerically. Okay. And now if I look at y of x, and I look at the discontinuity of y across this. So you see this would have a bunch of poles. And these poles basically coalesce to a branch cut. As I look at the discontinuity across the branch cut, it's going to give me precisely this is not worth it. So rho of s can also be thought of as the expectation value of delta s minus si. 1 over n. Okay. It's roughly the expectation value of how many eigenvalues you can find in some little region. Anyways, I'm just telling you that basically the discontinuity here, this part actually tells you precisely the eigenvalue distribution. So if you want, you can actually compute this if you actually do this. And last year we checked this against some numerical data of a Monte Carlo simulation, and you could precisely match the curve. So that was very nice to see. Okay, it's just, yeah. For people who've heard of the Wigner semicircle, earlier we found that y looked like say, stuff times x squared minus 4. And if you want, that's precisely what this is. So this goes from -2 to 2. And this is the curve x squared minus 4. Okay? And that square root is precisely the discontinuity of y across the real axis. Anyways, forget the last 5 minutes, not important for you. If you got something out of discussion, it's great. I didn't. Maybe you answered some questions. Yeah, some random matrix theory. Okay, very good. Thank you very much, and we'll do some more TR.